In a direct current circuit, electrical current flows uniformly through the entire cross-section of a conductor. Every part of the wire, from the center to the surface, carries an equal amount of charge. However, with alternating current, the distribution changes. As the frequency increases, the current tends to avoid the center and flow primarily along the outer surface, or the skin of the conductor. This happens because of electromagnetic induction. Current flowing through the conductor creates a magnetic field. The magnetic flux linkage is highest at the center of the wire and lowest at the surface. The changing magnetic flux induces small loops of current called eddy currents. At the center of the wire, these eddy currents flow in the opposite direction of the main current, creating resistance. Because the eddy currents oppose the main flow in the center but reinforce it near the surface, the total current is displaced outward. This effectively reduces the usable area of the conductor. We measure this phenomenon using the skin depth, represented by the Greek letter delta. This is the depth at which the current density has decreased to approximately 37% of its value at the surface. The skin depth is inversely proportional to the square root of the frequency. As the frequency of the AC signal goes up, the skin depth becomes smaller, and the current is squeezed into a thinner layer. Since the effective cross-sectional area through which current flows is reduced, the AC resistance of the wire becomes much higher than its DC resistance. This leads to greater energy loss through heat. Skin effect is also influenced by the material. High conductivity and high magnetic permeability both decrease skin depth, meaning magnetic materials like steel experience a much more pronounced skin effect. To combat this, engineers use Litz wire, which consists of many thin insulated strands, or hollow tubes for high-power applications, as the center of a solid wire would be useless weight and cost. In summary, the skin effect forces AC current to the surface due to internal magnetic flux. Understanding this is crucial for designing efficient power grids and high-frequency communication systems. By optimizing conductor geometry and material choice, we can minimize the losses caused by the skin effect. This lesson was generated by Vision Solve AI.